Hello, students. This is Tanya Chu, and I'm going to guide you on the paper 5, second question with code 9702/05. It is about error calculation. Yeah. So okay, you know that paper 5 consists of 2 questions here. So the first question is about designing question, and the second question is about the error calculation. So my advice is whenever you receive your paper 5, always start with second question first. And make sure that you finish your second question, which is your error calculations, within 20 to 25 minutes. Yeah, so allow yourself to finish the second question within 20 to 25 minutes, and the rest of the time, which is about 50 minutes, will go to your first question because you need to use longer time for the first question. Yeah, so the second question is about error calculation. So we are going to use a little bit about your AS knowledge. Yeah, the error calculation, the absolute uncertainties, the percentage uncertainties, as well as the fractional uncertainties that you have already learned in AS. Yeah, so you know that the second question is the question that with errors, because our measurements are not accurate most of the time due to your systematic errors, due to your random errors, etc. So therefore, yeah, our results are not so accurate most of the time. So therefore, in second question, we are asked to calculate some errors here. So errors, we talk about uncertainties. Yeah, errors, we talk about uncertainties. So your uncertainties, you have three uncertainties actually. So you have absolute uncertainty. Let me refresh a little bit about this absolute uncertainty. And you have fractional uncertainty, as well as percentage uncertainty. So your absolute uncertainty, you have to bear in mind that it can only take one significant figure, like the one that you have learned in AS. So we are going to use that, even though the mark scheme is a little bit lenient on that, but I'm going to stick to that. Yeah. So I'm going to put all my absolute uncertainty to one significant figure only. Yeah, to simplify my working. Yeah, to avoid some careless mistake that I might be making. And the fractional uncertainty can take 1 to 2 significant figure. Percentage uncertainty can take 1 to 2 significant figures here. So in paper 5, second question, we talk about error bars as well. So error bars. So you have 2 error bars. First one is called vertical error bar. The second one is called horizontal error bar. Yeah, so how are you going to draw your error bars here? So the vertical error bar can be drawn like this. Yeah, 2 horizontal line and a vertical line in between. And or you want to draw in this way, there's also possible, or you would like to draw in this way. Yeah, it depends. Yeah, I will always prefer the first one. This is the one that I prefer to draw. Yeah, a horizontal error bar. Yeah, it's like this, or like this, or could be like this as well. It depends, and I prefer the first one. Yeah, so the error bars is due to some errors that we make during the experiment. Yeah, so let us look at our one of the past year questions so that it's easier for me to guide you here. So okay, this is one of the past year question here, so I'm going to read out the question here. So a student is investigating how the period of a simple pendulum depends on its length, as shown in figure 2.1 here. the time for 10 oscillation. You know what I like to do is that I like to underline, or I like to highlight the important statement that they give, important numbers, yeah, that might be useful to me later. So it's recorded for a pendulum of length L. The period T of a pendulum is determined, and the procedure is then repeated for different lengths. So let us go straight to the question here. So it is suggested that T, which is a period, and length are related by the equation T equals AL to the power of B, where A and B are the constant. A graph is plotted of log T on the y-axis. Can you see that they are very clear on that? They told you the y-axis, and log L on the x-axis. Determine expressions for the gradient and the y-intercept in terms of A and B. So you have, when the equation is given, and they have already told you what type of graph that they are plotting on both x-axis and the y-axis. So you have to modify the equation to suit, yeah, whatever is plotted on the x-axis and y-axis of the graph. So I will write down the equation first. T equals AL to the power of B here. And since this is log T is plotted, so very simple, just put log on both sides. Log T equals log A plus power, just put to the front, log L. Can you see that? And they told you that log T is your y-axis, log L is your x-axis. This is your x-axis, this is your y-axis, okay? And you know that this is a straight line, yeah, graph. So this is my y-axis, this is my x-axis. And can you see that? Okay, back to the straight line equation. General equation of straight line is y equals mx plus c here. So the m must be beside the x. So my m, which is a gradient, is my b. So I just, oh, sorry. So my gradient is actually b. Yeah, so I'll just put here b. Yeah, and of course, mx plus the whole thing here, log A, represent the y-intercept, which is c. So just write down, oh, sorry, it's log A. So you just write down log A. As simple as that, and you could score 4 marks. You could score full mark for that, yeah? And part B here, values of T and L and T are given in figure 2.2. Okay, let us look at the instruction given. Calculate and record values of T, which is a period, slash second, that is the unit of period, log L, log T. And in figure 2.2, include the absolute uncertainties in log T. Yeah, I'm going to teach you the easier way to calculate the absolute uncertainty in A2, yeah, paper 5, second question. We are not going to use AS method here. I'm going to use only, okay, A2 method, I call it. So look at the number of oscillations here. There are 10 oscillations here. So period is equal to the total time taken for n number of oscillation. Can you see that the number of oscillation is 10 here? So the total time, okay, are actually given here. So 19.6, very simple, make it simple. So period, yeah, period is equal to T over 10 because number of oscillation is 10. So 19.6 divide 10, I get 1.96, 1.84, 1.74, 1.62, 1.48, and 1.34 here. Can you see that? It is that simple. Yeah, and you have to calculate the value of log L as well. You just take out your calculator, press log 95, press log 85. You need not have to change the unit to meter. As you can see here, the unit is in cm as well. Yeah, so if you get the correct value here, it should be, yeah. Before that, you have to bear in mind log L is calculated from L. Yeah, so when we talk about calculated values, we look at the significant figures of our raw data that we use to calculate that. Yeah, so my raw data or my raw reading would be L. L has 3 significant figures, so all my log L values will follow 3 significant figures. Yeah, so I get 1.98 here, 1.93, 1.88, 1.81, 1.74, 1.65 here. Yeah, and they also ask you to calculate log t together with the absolute uncertainties in log t here. So my advice is, this is how I do it. So since the absolute uncertainties must be included in log t, very simple, I'll just write plus minus for every column here first. Put all the plus minus there, and then how am I am doing my delta log t first. Look at the t values here. Look at all my t values here. So my t values, especially the first one, 19.6. This is my t value, 19.6 plus minus 0.2. It means that 19.6 is the average value of t that spread out between the two extreme values, which are 19.8, you just plus 0.2, and 19.6, you just minus 19.4, you just minus 0.2 here. So your period, the period that you calculated here, must have the absolute uncertainties as well. It's just that they asked you not to conclude that, not to put in. They didn't ask you to put in that. So therefore, I am looking at my t value here. So my t value is depending on the raw data, which is a small little t here, over 10. So since all my period values are divided by 10, so all the absolute uncertainties of the time taken must be divided by 10 as well to give the uncertainties of period. So actually the one that I'm writing in black are the one that you don't need. It's just that I write it here so that it's easier for me to do it. So 0.02 here. So all the readings of t are included with the absolute uncertainty of 0.02 here. It's just that you don't write it down. So the simplest way to do this question here, to find the absolute uncertainty of log t here, delta log t, you just do it this way. Okay, I'll just put log t, a larger value of log t minus log t average. You get what I'm trying to say? The one that we wrote there, 1.96, means the average value of the period. So the larger value of period here, you can see that from here, period is equal to 1.96. This value is the average value of period that spread between two extreme values, which are plus minus 0.02 plus 0.02 minus 0.02. So that means you have 1.98 and 1.94. So how you do it is that, you just take a larger value, because I prefer plus positive. So I'll just take this larger value minus my average value. That's simple. So I'll just take 1.98 minus 1. I mean, not 1.98, it's actually log 1.98, because if it is a log, you have to log the value. If it is a square root of t, delta square root of t, then you have to take square root of larger t minus square root of smaller t. If this is a cube root or a cube, delta t cube, so you just need to take the t larger t cubed minus the average t cubed. That's simple. So I'll just take my log 1.98 minus log 1.96. So if you get it, type it into your calculator and make sure that this is what I did. I make sure that all my absolute uncertainty, I put it in one significant figures. Yeah, even though the mark scheme is not so strict about it. Yeah, but I do it that way. It's easier for me. Yeah, so I put it in 0.004. So 0.004 here. Yeah, the same goes to the second value of t, which is 1.84. You just take 1.84 plus 0.02, which is 1.86 minus log 1.86 minus log 1.84, and it will give you 0.005. Yeah, the third one will give you 0.005 as well, and fourth will give you 0.005, 0.006, and 0.006 here. Yeah, after I have done calculate my absolute uncertainty of t here. So what am I going to do is that, yeah, okay. What am I going to do is that I'm going to calculate, yeah. What am I going to do is that I'm going to calculate all the log t value. Yeah, so delta log t slash s here. So I'm going to calculate all my log t value, and all my log t values will follow the decimal points of my absolute uncertainty of t. Yeah, so the first one I will have 0.292, second one 0.265, 0.241, 0.210, 0.170, and 0.127. Yeah, so we are done with the tabulation of the table. We are filling all the information that we need here. So the third part, which is part C, you have to plot a graph of T against L, and you have to include the error bars. And before that, I have told you that we have two error bars. One is horizontal error bars, and the other one is vertical error bar. How do you know which is whether you are supposed to plot the vertical error bar or the horizontal error bar? Very simple. Look at the question again. Yeah, look at the question again. The question told you that this graph is supposed to be the graph of log t against, yeah, let us check the graph. Yeah, yeah, this graph is about log t against log L, and the uncertainty, all your absolute uncertainties are all the log t uncertainty. Can you see that log t represents y-axis? So therefore your error bar has to be vertical error bar. Yeah, you just plot, okay, just plot your graph. The graph is actually given. This is a graph that I have plotted. So yeah, you just need to plot your best fit line, yeah, just like normal, and yeah, and find the gradient just like normal as well. And then you have to plot your worst fit line. Yeah, some will ask me how to plot the worst fit line. Now, since you have the error bars, yeah, so yeah, your error bars, when you plot your error bars, so let us look at the first value of my error bars here. My first value of the error bar is 0.292 and 1.98, which is here. Yeah, so this is my first error bar. So the first error bar is 0.004. That means the height of the error bar must be 0.04. So based on the point, yeah, the coordinate that you take, yeah, the coordinate that you plot here, you have to make sure that, okay, let's say this is a coordinate that I plotted, and you have to make sure that, yeah, start from the center of the x here, yeah, the height of the error bar must be 0.004, and start from the center as well, going down, yeah, it has to be 0.004. So that means, yeah, the length of the error bar would be 0.008. Yeah, you get it? So same goes to all the error bars. Yeah, and to plot your worst fit line, so let's say I'll just say this is your, okay, I'm going to plot my best fit just beside it. Yeah, let me plot my best fit first. Okay, so I'll just say that So let's say that, okay, let's say, for example, I just take one example. I'm just going to plot beside this graph that I have already plotted. So your graph is roughly like that one. So let's say, yeah, this is my best fit line, for example. Yeah, let's say this is my, yeah, this is my best fit line. Make sure that you label it as best fit line. Yeah, so I label it as BFL here, best fit line, but I have to explain, yeah, what is BFL means, where, yeah, BFL means best fit line. Let's say these are all my points, for example, yeah. So, yeah, and those are my error bars, for example, as well. These are my example, yeah, the example. So use a ruler if you want to plot a best fit, a worst fit line. Yeah, all you need to do is just to look at the first error bar and the last error bar. Yeah, so the first error bar you look at, if you start at the tip of the first error bar, you have to end at the tail of the last error bar, and the straight line graph that you draw must be passing through all the error bars in between. Yeah, so if you start from the tip of the last error bar, you have to end at the top of the last error bar. Yeah, if you start at the tip of the first error bar, you have to end at the top of the last error bar, and make sure that the worst fit line that you are about to draw must be crossing all the error bars in between. Yeah, so I'm going to use my ruler again. Yeah, so I'm going to, yeah, tilt my ruler a little bit here. So tilting, yeah. So let's say, yeah, because this is just a sketch. Yeah, so let's say this is my worst fit line that I'm supposed to draw. Okay, so I'm drawing my worst fit line here. Yeah, put back my ruler. Can you see that this is my worst fit line? And my worst fit line is actually passing through the error bars in between. Yeah, the first and the last error bar, and I labeled it as worst fit line. Yeah, so back to the question again. They will ask you to find the gradient of best fit. Yeah, they will ask you to find the gradient of the best fit. Draw the straight line of the best fit and the worst fit, and on your graph both lines should be clearly labeled. Make sure that you label, yeah, the two lines, and determine the gradient of the line of best fit. Include the uncertainty in your answer. So when you are asked to determine the gradient of the line of best fit, is very simple. We just use the y2 minus y1 over x2 minus x1. So that is the normal way to find your gradient. But to determine, since you are asked to include the uncertainty in your answer, uncertainty of the gradient in your answer, so you are supposed to calculate the gradient of the worst fit as well. Yeah, so based on the line of worst fit, calculate the gradient of the worst fit. So you get a value of the gradient of the worst fit, and you get a value of the gradient of the best fit here. Yeah, so the uncertainty of the gradient is very simple, delta m. So you just take, I put a modulus here because I want a positive answer. You just take a bigger value, bigger gradient minus the worst fit gradient. Yeah, so get your answer, just like that. Yeah, so I always put it in one significant figure for my absolute uncertainty. So I put one significant figure as well for my absolute uncertainty of the gradient. Yeah, same goes to your y-intercept. If you're asked to find the uncertainty, you just take the best fit, yeah, the y-intercept of your best fit, put a modulus because you want a positive number, minus the best fit of, the worst fit line, the y-intercept of the worst fit line, and put it in one SF because I did that. Yeah, so now I wish you all the best in your paper 5 second question, and I hope the video will help you to boost your mark, yeah, confidence in your paper 5. Bye, see you again.